24 questions from this textbook. That's what I'm doing, teaching physics by picking just 24 of the problems and solving those problems. So right now we're on problem number 11, chapter 12. So I skipped chapter 1. I'm not going to do every chapter. I didn't say chapter. I said problem. 24 problems. I picked 24 problems. So we're in chapter 12 in this textbook, Halliday Resnick and Walker, 9th edition. The title of the chapter is Equilibrium and Elasticity. So let me get to the problem, and then I'll talk about those two things, and then we'll do the problem. So the problem is number 54 from the chapter, and there's a ladder leaning up against a wall. It's a frictionless wall, which is very important, otherwise it makes it very difficult. And we know the coefficient of friction on the ground. The question is, how far can you put the base of the ladder from the wall and not have it fall over? So that's the problem we're going to solve. So how do we solve it? Let me briefly talk about elasticity, because I'm not going to really use that in this problem. So I'm not going to go over all the equations. There's not that many. Imagine this was a metal wire and I pull it. It's going to stretch, right? The metal is a little springy, so it's going to stretch. I could compress it too. If I make the wire thicker, it's going to stretch less. It's going to be harder to, it's going to be stiffer. If I make it longer, it actually makes it more springy. So there's a way to kind of undo those two properties, the physical properties of the wire, by incorporating both the length and the area. And this is a property called Young's modulus. It tells you how stretchy the material is independent of the actual shape. So that's the whole thing about Young's modulus, not using this problem. And I'm not even sure why it's in this chapter, because it doesn't really go with equilibrium, but whatever. And it is important in a lot of engineering applications, stuff like that, but it's not like a super fundamental thing as much as equilibrium is. We're going to talk about equilibrium. So when we talk about equilibrium before, let me start off with an example. Suppose you put a pencil on the table and you push with the force F that way and a force F that way, and it's just going to stay there, right? We know that. However, what if you pushed right here and right there with equal and opposite forces? Yes, the net force is 0, but it's not going to be in equilibrium. The thing's going to rotate. So in order to say an object's in complete equilibrium, we actually have two conditions. So the two conditions for equilibrium are this: the net force is equal to 0, 0 vector. Remember, you can't have a scalar equal to a vector. And the net torque about some point O is equal to 0. Now, just a quick reminder, torque about some point O is R cross F. Now, if we're dealing with just the magnitude of the torque, we can write torque O as R F sine theta, where theta is the angle between R and F. Now, sometimes it's easier to write this as R perpendicular F or R F perpendicular. So this says take the perpendicular distance from the force to the point O and multiply them together. It's the same thing as R sine theta. Or take R and the perpendicular force. Either way works. Okay. Those are two very useful ways of calculating torque in two dimensions. Now, that's the scalar value. It's actually a vector. So if you use your right-hand rule, this says that if the torque would make it rotate that way, then it's a negative. Clockwise is negative. Counterclockwise is positive. I mean, it's not super important. If you switch those, the problem will still work as long as you're consistent. So this is actually 2 or 3 equations, right? We're going to deal with this as 2 equations. I'm sorry, this F net x and F net y are 0, and then torque net is 0. Now, about that torque 0, or O, right? So if I have the net torque is 0, that means that the rotational motion, the angular motion is, angular acceleration is 0. And if it's not rotating, it stays not rotating. Now, if I pick this point right here to calculate the torque, I can do that, and it works. But if it's not rotating about this point, it's not rotating about that point, it's not rotating about that point. So you can actually pick any point that you want to find the torques. Okay, torque does depend on where you calculate it from. Okay, one more thing. Center of gravity. If you have a stick, it's made up of mass. And every single part of that mass, every proton, electron, and neutron experiences a gravitational force due to interaction with the Earth. It's true, okay? But we don't want to calculate all those forces. So it's possible to replace all of those forces on the ruler with just one single force where we use the total mass and the gravitational field, and this is at the and we apply it at a location of the center of mass. Okay, so it turns out that we call that the center of gravity. The center of gravity is equal to, in the same location as, the center of mass if g is constant. Okay, if g is not constant, that's not true. You're not going to see any non-constant g problems in this book, but I just want to let you know. I'm trying to tell you the truth, right? I don't want to lie to you. I think that we are ready to do this problem. So we have this ladder leaning up against the wall, and it's just about to slip, right? We want to put it as far away as possible so it's just about to slip. And that means it's still in equilibrium. So let's set up the equilibrium conditions for this leaning ladder. I'm going to start off by drawing the ladder. And drawing all the forces acting on it. So we have the gravitational force. It acts at the center of the ladder. If the ladder is uniform density, then the center of the ladder is the center of mass, and since the gravitational field's constant, that's the center of gravity. Okay. Now, what else is acting on the ladder? Well, we have this wall pushes on it. I'm going to call that force N1. It's a normal force, and it's perpendicular to the wall. So the wall's vertical, that means the force is pushing that way. The floor is pushing on it. And now the floor is horizontal, so it has a normal force pushing up. I can call that one N2. And you can see right here that that can't be it, right? I have to have another force because I can add up forces in the x direction to be equal to 0, but I only have that one force in the x direction. If that's it, it can't possibly be in equilibrium. So we have another force, and it's the frictional force down here. I'm going to call it F. It's static friction, but that's fine. Okay. I think we're ready to go ahead and write down our conditions for equilibrium. So I have here F net in the x direction is 0. F net in the y direction is 0. And then torque net about some point O is 0. Now, x and y also are made up things. We can pick whatever we want for the x and y direction. I'm going to pick the obvious x and y. So let's just do the forces in the x direction. I have friction in the positive x direction, F friction. And then I have this normal force N1 in the negative x direction. That's easy. In the y direction, it's also easy. You have the normal force N2 pushing up and gravity down. N2 minus mg. Now, for the torque, I can pick whatever point I want. There's three locations we could consider. Remember that the torque is RF. And so right here, if I pick that as my torque point O, then R for this force is going to be 0. So this force is not going to have a torque, and the value of N1 will not be in that equation. Maybe that's a good idea. If I pick right here, then the gravitational force will exert no torque, and it won't appear in the equation. Finally, if I pick down here, neither of those two forces will be in the equation. So because there's two forces there, I'm going to pick that. So those two forces will not be in my torque equation. Now, you can pick any location, and it will work, okay? But just some ways are easier than others. So I'm just going to pick that one because I get rid of two forces. So I'm going to write down the torque equation. Gravity would make it go clockwise, so that's a negative torque. That's a positive torque. So let's look at that one first, because I can write positive first. So it's going to be the force in 1, and then I get the perpendicular distance. So here's the distance, but this right there is the perpendicular distance, or this is the perpendicular distance. See, now that distance and that force are perpendicular, so I can use that. So I can just find this distance right here. Now, the problem didn't give it, but I put an angle theta right there so that we can solve for the value of d. So that's my angle theta. And if that's the angle theta right here, and this is the length, I'll call that L, then this would be L sine theta. So I have N1 L sine theta. Now, for the gravitational force, I'm going to do the same thing. It has a negative torque, negative. The force is mg. And this distance right here is going to be the perpendicular torque arm. So this hypotenuse of that triangle is L over 2. And I'm dealing with the adjacent side here, so it's going to be cosine theta. So now you see I have 3 equations, and I don't know the friction. I don't know N1, that's two things. I don't know N2, that's 3 things. And I don't know theta, that's 4 things. So I have 4 things that I don't know, and I only have 3 equations. So that means I need another equation. Well, I can do that. So, and also you'll notice that these equations do not have the thing that we want, which is d. So let me address that question first. So if this is the distance d, the distance from the wall to the ladder, I can get an expression for this in terms of L and theta, right? Because I have the adjacent side of a triangle here. I can say d is L cosine theta. So if I find theta, I can find d. That's important. Next, if we're dealing with the maximum location of the ladder, then we're dealing with maximum friction. For maximum friction, I can say the frictional force is equal to the coefficient of static friction times the normal force, this normal force, N2. Now remember, static friction actually is less than or equal to, but we're at the maximum, so it's equal to. Okay, so let's go ahead and put this in for the frictional force, and then I get the following. I get I'm going to put an arrow, it's not equal to. Arrow, N1 equals mu s N2. Right, that's what I get right there. Now, this equation, I get, I can solve this for N2. Remember, it's still equal to 0. So N2, I'm going to put an arrow, it's not equal to. N2 is equal to mg. So that means up here, N1 is mu s mg. I just did 3 substitutions right there. Now, if I put in up here, you see how this is a super easy system of equations to solve. I didn't even really need to try, and I'm getting what I want. So if I put in for here, I get, I'm going to move that to the other side. I get mu s mg L sine theta equals mg L over 2 cosine theta. I know mu, I know m, I know g, I know L. I don't know theta, I don't know theta. So I need to solve for theta. Well, here we're going to have to do some trig, right? I can divide both sides by cosine theta. And then I have sine over cosine. And sine over cosine is tangent. So now I'm going to divide both sides by this, and I get tangent of theta is mg L over 2 mu s mg L. That stuff cancels. I get 1 over 2 mu s. So now I can find theta. Theta is just going to be the inverse tangent of 1 over 2 mu s. If I put in my numbers that give a coefficient of friction of 0.46, notice it doesn't depend on the length, it doesn't depend on the weight, right? Those things canceled. So I can put that in my calculator and I'll find the value for theta. So let's do that. Calculator. Drop, drop. So I have 1 enter 2 divided by 0.46 divided by inverse tangent. I get 47 point, let's say 39. Now I can go back over here. D is going to be, the length of the ladder is 5, cosine 47. So if I put that in here, I already did it. I did it before and I had a technical error, so I left it in there. 3.39 meters is the answer. So there you go. I think it's a pretty good basic equilibrium problem. You can definitely get things that are more complicated than that, but that's where we are. So some bookkeeping notes here. Playlist for this whole 24 questions things down below. We're getting close to the halfway point. That would be your first semester of physics, and different courses cover different things. You may not do rotational equilibrium. I don't know, but I'm just trying to do what I would kind of do with that book. So there you go, 24 questions. I'll see you in the next question.